Hello and welcome to CPH Session 19, Inferential Statistics, Making Comparisons and Conclusions from Data. This is Part B, Sampling Variability and Confidence Intervals. In Part B, we're going to define sampling variability and the standard error. Then we'll use those definitions to learn how to compute confidence intervals for our samples. And finally, I'll tell you what to do in cases when your sample size is small. Before we begin though, I want to talk one more time about the mean. This time we're going to consider the mean as a simple statistical model for our data. The mean is a statistical model for two reasons. First, it's hypothetical. If I ask 10 college lecturers how many friends they have, I might find that the mean value of my sample is 5.7 friends. Of course, unless you're the Texas Chainsaw Murderer, I doubt anyone can have 5.7 friends. Thus, it's hypothetical and not necessarily exactly representative of any real situation. Secondly, we can use the mean to describe a real-world phenomenon. My mean of 5.7 friends is our simplest and best way to describe the number of friends that these college lecturers have. It's a way to describe and possibly predict this real-world situation. How well does this model describe the reality? Well, let's consider two different realities. In the first sample, I asked 10 college lecturers how many friends they have, and this is what I see. The mean is 5.7 friends, and my mean does a pretty good job of describing reality. Most people have around 5 or 6 friends. On the other hand, in example B, we see that the sample also has a mean of 5.7 friends. However, that mean really isn't a very good model because nobody has 5 or 6 friends. In fact, most of them have much more, much less. So how well our statistical model describes the phenomenon and how closely it matches reality is called the model's fit. Sample A's model has a pretty good fit. Sample B's model doesn't have a good fit. We can even quantify how good a model fits our data. Often we use the sum of the square of differences. So in other words, we compute the difference from our model to the observed reality. We square that difference and then add it all up. So if you remember, that's the first thing we do to compute the standard deviation. So the goodness of fit for our mean can be represented by the variance or standard deviation that we talked about in session 18. Sample A has a smaller standard deviation than sample B, which indicates the data points are closer to the mean, and therefore the mean is a better model for that data compared to in example B. Another way to understand how the mean is a statistical model is to understand that a model, any model, whether we're talking about statistical models, economic models, or water quality models, can be expressed this way. The outcome is equal to the model's prediction plus an error. Applying this concept to the mean, we see that any single observation can be equated to the mean, our model's prediction, plus the deviance of the observation from that mean. In the example of my survey of how many friends the college lecturers had, one of my participants had 4 friends. In that case, my model said college lecturers have 5.7 friends, and the deviance or error of that observation from my model was negative 1.7 friends. But usually we don't take a sample with the intention only making conclusions and descriptions of that sample. Usually we take a sample with the aim of making some conclusions about the population as a whole. In that case, we're trying to infer something from our sample. We've seen that the standard deviation tells us how well our mean describes our sample. But what if we want to know how good a fit the sample mean is of the population from which we took the sample? To answer that question, I'll go through an exercise to illustrate it to you. So imagine an entire community of 1,000 adults in a Thai village. That village has an HPH. And each of the 1,000 adults has an opinion of the quality of services provided at the HPH. And also imagine that there exists a questionnaire that has a set of Likert items that we can composite into a Likert scale, and that scale goes from 1 to 5. And we also know that it's a valid way to measure that opinion about the quality of service at the HPH. Now, we also know, because we have supernatural omnipotent powers, that the entire population of 1,000 adults has, on average, a middle-of-the-road, not great but not bad, opinion of the quality of service. On our Likert scale, that's represented by the number 3. Now, imagine I randomly picked out 20 people from the population, and they took the questionnaire. I then computed the mean of Likert scales from that sample and found a sample mean of 3. Then, I randomly picked another 20 people, and this time, the sample mean opinion was 2. And let's say I kept doing that for a total of 9 samples of 20 people each. And some of the sample means were as low as 1 and as high as 5. This represents sampling variation, and it also demonstrates sampling error. Sampling variation is the differences that you find in summary statistics from one sample to the next because each sample contains different members of the same population. And sampling error is the difference between a sample's summary statistics and the population's true value because a sample doesn't completely represent the entire population. So samples will vary because they contain different members of the population. As an example, a sample that by chance includes people with a high opinion of the HPH will have a higher sample mean. Now, if we make a histogram of the sample means, we see that it looks normally distributed, and it's centered around 3. This is called a sampling distribution. Sampling distribution is the frequency distribution of sample means from the sample population. Now, of course, you have to imagine that you're taking hundreds or thousands of samples to construct a real sampling distribution and not just the 9 samples that I did to illustrate my point. We can also see that this sampling distribution has a standard deviation. And that standard deviation of the sample means tells us how much variability there was between each sample. That's called the standard error. The standard error is the standard deviation of all the sample means. However, we usually don't have the time and the resources to take hundreds or thousands of samples. Usually we only take 1 sample. So how can we estimate the standard error? Well, some enterprising statisticians discovered what we call the Central Limit Theorem. It tells us that as long as the sample size is larger than 30 or 60, that the sampling distribution is normally distributed. It also tells us that the mean of our sample means is equal to the mean of the population. And it tells us that the standard deviation of the sample means, or the standard error, is equal to the population standard deviation divided by the square root of our sample size, which in the example I gave you was 20. So the central limit theorem gives us a way to compute confidence intervals, just as long as the sample size is large. Generally, statisticians mark the boundary between a small and a large sample at either 30 or 60 people. Why? Well, it's because as your sample size gets less than 60, and definitely once it's less than 30, the sampling distribution no longer is normally distributed. And so our central limit theorem needs a tweak. And we'll talk about that at the end of this part B. So, what is a confidence interval? A confidence interval is the boundaries within which we believe that the true value of the population mean will fall. I'll illustrate that using a study that collected sperm counts from Japanese quail. Yes, the birds. It turns out we know that the true population mean. We know that the true population mean sperm count of Japanese quail is 15 million. Just imagine we know that. Now, let's start taking samples from that population. In the first sample that we take, the mean sperm count was 16 million. And they computed a confidence interval, and it went from 5 million down up to 27 million. Now take note that 16 is right in the middle. The scientists, or maybe the quails, enjoyed the experiment so much that they decided to take another sample, selecting quails again from the population. This time, the sample mean was 18 million. Again, they computed a confidence interval, and this time it went from 11 million to 25 million sperm. Remember, the confidence interval tells us the range in which we believe the true population mean falls. So fast forward to the point where they've completed the experiment 50 different times, taking 50 different samples and computing 50 sample means and 50 confidence intervals. Here's a visualization of those experiments. It turns out that most of the time, the true population mean, remember it's 15 million, falls within our sample's confidence intervals. However, in 3 out of the 50 samples, it did not. So what that means is that in 94% of our samples, the confidence interval captured the population mean. That's pretty good. Now, I haven't yet mentioned to you that in this case, we're specifically talking about 95% confidence interval. That's what the scientists were calculating, and I also haven't told you how the scientists actually computed that interval. But first, just remember this whenever you see a 95% confidence interval. If we had collected 100 samples, calculated the sample mean for each of the 100 samples, and then the 95% confidence intervals for those means, kind of like what I showed you with the quail sperm, then for 95 out of those 100 samples, the confidence intervals that we constructed would contain the true value of the mean in the population. Now, to calculate a 95% confidence interval, we find 1.96 times the standard error. That is, 1.96 times the sample standard deviation divided by the square root of the sample size. And our interval is plus or minus away from the sample mean. Let's practice with an example. A group from the CDC looked at medical spending records for more than 10,000 U.S. patients to study annual expenditure on healthcare among those with a history of smoking and those without a history of smoking. The mean, standard deviation, and the sample size of the 2 independent samples are shown in this table. Looking at the results, we see that smokers in our sample spend more on average than our non-smokers. But let's compute the 95% confidence intervals for each of the 2 samples. How can we do that? Well, we need our formula. For our group with a history of smoking, we put our numbers into the formula and we find that 1.96 times the standard error, it works out to be $117. So our confidence interval is this. It goes from $2,143 up to $2,377. For the group without a history of smoking, 1.96 times the standard error works out to be $127. And so our 95% confidence interval would be this. So let me ask you, looking at these results, do you think smokers spend more than non-smokers? Based on these results, it would not be wise for us to assume that smokers spend more, even though their sample mean was higher. Why? Because the 95% confidence intervals overlap. Here, I've charted the mean and the 95% confidence intervals, so the dot and the bars, of our 2 samples. We can see it's quite likely that the true mean spending of smokers is in this range, and the true mean spending of non-smokers is probably in this range. So because they overlap, it's plausible that the two samples came from the same population. That is, it's possible there is no real difference in the two groups. Perhaps they're really the same population. Now, if they did not overlap, we could explain it two ways. First, it might suggest that the two samples came from two different populations, smokers and non-smokers. Or, secondly, both samples came from the same population, but one of the confidence intervals doesn't contain the population mean. Now, since we use the 95% confidence interval, we know that the second explanation is unlikely. It would occur only in 5 out of 100 times. So all of this, what we're doing here, is the basis of hypothesis testing, which we'll cover in later parts. But at this point, I just want you to be able to compute and interpret confidence intervals. But our examples so far had a big sample size. And I mentioned earlier that our central limit theorem breaks down as n gets smaller. So what happens when n gets small? That formula I gave you isn't going to work. If you remember the sampling distribution, when I took many samples about the villagers' opinions on HPH quality, I said that according to the Central Limit Theorem, the sampling distribution is normally distributed. However, once n is smaller than 60, the shape of the sampling distribution starts to change. And as n gets smaller, and once n is smaller than 30, its shape is definitely no longer that of a normal distribution. Instead, its shape is what we call a t-distribution. The t-distribution is like a smushed version of the normal distribution. In that case, we can't use 1.96 in our 95% confidence interval formula. Instead, we replace the 1.96 with the t value, and we have to look up the value of t in a table depending on the degrees of freedom. Degrees of freedom in our case is just n minus 1. So, for example, if our sample size was 11, our degrees of freedom is 10. So the confidence interval would be plus or minus 2.228 times the standard error. As you can see, because our sample size got smaller, our t value got bigger, and that means our confidence interval got bigger. Now all of this is starting to get complicated, and I've got good news. We can use Excel or SPSS or any statistics program that you choose to do the work for us. And before I show you to do that, I'll just mention one more thing, that the 95% confidence interval is certainly the star of the statistical world, but it's not the only game in town. The confidence interval that we use depends on our desired level of significance, and we call our significance level alpha. And the confidence level is just 1 minus alpha. So a significance level alpha of 5% is associated with the 95% confidence interval. However, some clinical studies require an alpha of 1%, which means they look at the 99% confidence interval. And on the other hand, more cursory studies might require an alpha to be 10 or 20%, so the confidence interval of 90 or 80% respectively. The last thing I'll do is show you how to do this in Excel. So in Excel, we can use the confidence.norm function. It requires 3 inputs. It requires alpha, the standard deviation from our sample, and the sample size. So, and if your n is less than 60, we need to use the confidence.t, and it has the same syntax. As an example, you could calculate the lower bound of the 95% confidence interval from the smoking example. So in any cell in Excel, just type equals sign, and then 2,260, which was the mean from that sample, and then minus sign, and the formula exactly as I have written here. So I give it our significance level that we want, which is 0.05. I give it the sample standard deviation, and I give it the number of people that were in our sample. And after you hit return, you should get a result of around 2,143. So at this point, you should be ready to finish question 2 of the session 19 practice worksheet, and we'll see you there for part C.